Today we're going to talk about conductors and insulators, and we're going to talk about work and what work is when we're talking in scientific measures. So the first little part isn't that bad. It's about a page of notes. Actually, it's less than a page. We're just going to identify like what conductors and insulators are, and then you're going to give me 3 examples of each. When we get to that slide, there's going to be a whole slide of conductors and insulators you can choose from. Just pick 3. And then when we're going to get into what work is, which is not what you're thinking of. And then how to calculate work and how to provide evidence that work has occurred. So let me see where you are. Here it is. So we do know from last week that heat is transferred in 3 different ways. It's transferred through conduction, radiation, and convection. Conduction is whenever it's transferred through touch, and convection is through a fluid like a gas or a liquid, where we have the rising of the heated fluid and then the sinking of the cooled fluid, and it creates these like little cells of moving heat. And then radiation is the transfer of heat through an open space in the form of like rays or waves. So like the electromagnetic rays that the sun sends heat to the earth through. So anyway, when we're talking about how like through materials, how heat is transferred, you guys already know this, but there's 2 types of materials that transfer heat, or if you're an insulator, don't transfer heat. And those are conductors and insulators. I'll give you a second to look at that little comic. But conductors are materials that easily carry heat. And these are things that heat up quickly, and they also cool down quickly because the heat moves easily through that material. So it's kind of like when we were talking about global winds. No, I'm sorry, not global winds. Oh my gosh, sea breezes. Sea breezes and land breezes, they're formed because sand releases and gains heat energy quickly. So, and then the water holds on to heat energy and it gains it slowly. So it creates this uneven heating in a smaller area, and it creates these wind patterns. And it's because sand is more of a conductor than water is. So that was fun. Little spin. Here, you don't have to write down this example. On the next page, it's going to be a whole like slew of examples. But when you put a metal pan on a heated source, it'll get hot really quick. And that in whatever material is inside of that metal pan, it will also gain heat energy quickly. Most of conductors are going to be metal, so any sort of metal material is going to be a conductor. Glass, water is a conductor, but sand is more of a conductor than water, which is why we have those uneven heating situations when we're talking about land breezes versus sea breezes. And people and animals are conductors because we're composed of water. Trees are conductors, and then I don't know, that's kind of redundant that it says people are conductors and then it says you are a conductor, because we're all people. Anyway, so on the other hand, we have insulators, and these types of materials do not allow heat energy or electrical energy to pass through easily. It does. Some insulators will allow heat and energy or electricity to pass through, but it's a very, very slow process. So, for instance, these oven mitts, when you're taking something extremely hot out of the oven, if you're just like putting the oven mitts on and quickly grabbing the, let's say it was a pan of brownies out of the oven and then releasing it, you wouldn't feel that heat transfer. However, if you were to hold on to the heated pan of brownies for an extended period of time, the heat would begin to transfer from the pan to your hands. It would just take a lot longer. So, oh, there it is again, a little twirl. It's so much fun. Polar bears swim in freezing water, but they don't swim to death because they have a very thick layer of blubber, it's a fat that insulates the bear. So this fat is wrapped around the body of the bear, and what that does is it traps the heat inside the bear's body. So here are your list of insulators, non-conducting materials. Oh, any sort of plastic, porcelain, rubber, animal fats, wood, wool, styrofoam. It already says plastic. It's rubber or plastic. But see, there it is being redundant again on the last line. So anything made of rubber or plastic material is going to be a good insulator. So, when we're talking about whether materials or conductors or insulators, we're not, it's on a scale. So remember when I said that the land heats up more quickly and releases heat more quickly because sand is a better conductor than water? If you look at the scale and you have like the good conductors going this way towards aluminum and good insulators going this way towards polystyrene, you can see that stone and sand are on a scale. They're both insulators, but stone or gravel or sand would be closer to a conductor than water would. So it's just because something is a conductor or an insulator doesn't mean that it's the best conductor insulator. So let's see what's next. Is it going to let me just, nope. All right, so here's this activity. And we're actually going to go over this in class, but if you wanted to go ahead, you know what? No. You guys can go ahead and I'm going to put this in the ed puzzle, and you guys will put in the ed puzzle whether each material is a conductor or an insulator. So we have a penny, a piece of wood, a styrofoam cup, silver, frying pan, aluminum can, wool, paper, cork, trumpet, gold, rubber tires, a thermos, brick wall, leaf, and wool gloves. The reason I was annoying and named them all is because they look kind of blurry, and I wanted you to know which each one was. So you're just going to label conductor or insulator. Okay, so now let's talk about work. When we're speaking about work in scientific terms, work is when energy is used and transformed into kinetic energy. So work happens when a force is used to move an object. So in our little image here, we have Home Slice pushing a box up a ramp. He's applying a force to the box by pushing it, and the box is responding by moving. So once he moves, work is being done, and once he puts the box in place where it's supposed to be, he will have completed that work. So it's taking stored energy and transforming it into kinetic energy in order to accomplish movement. So let's look at some specifics. I just said that work is done when work is transformed into energy. Work is a type of energy. So when we have our work energy and transform it into kinetic energy, that's whenever we've accomplished work. So let's talk about lifting versus pushing and pulling. If we were to lift a heavy object, the amount of potential energy that it has due to its distance from the Earth's surface would correlate to how much work was done. So if we raised a bowling ball above our head, the amount of stored potential energy it now has being raised above our heads is equivalent to the amount of work done to lift it into that position. So they correlate to each other. I just said that. Oh, this is important. This last little third blurb. Uh, if we are using a tool to accomplish work, it's still the same amount of work. So, for instance, if we were lifting an object straight up, into the air, into position, where the same amount of work is being done if we had rolled the object up a ramp to get into that position. Even though one may be easier than the other, it was still the same amount of work accomplished because you moved that object from point A to point B, and it didn't matter how it happened, you still applied a force and the object moved by responding. So here's some examples of work being done. If you have a toy car and you push it, work is done if the car moves. And this is important, and it has to move in the direction of the force you applied. So if I push the car and it moves the opposite direction, which that doesn't happen unless you have one of those cars that when I was a kid, you could take a car and push it backwards and it would like gear up and like gain potential energy, and then when you released it, it would shoot off in the opposite direction. But if you push an object or push a toy car and it moves, you've accomplished work. Even connecting a fan or other object that has kinetic energy, once you connect it to a circuit and it begins to move, you've accomplished work because you've put potential, or you've taken work and converted it into kinetic energy. And when you lift an object, it moves, so work was done. We've already talked about that example. So there's a way to calculate and determine how much work was used to make something move. And the formula is work equals force times distance. You'd abbreviate it with W equals F times D. And let's do an example. So let's say a crane uses an average force of 5,200 newtons to lift a steel beam 20 meters. Force is measured in newtons. So when you see force being measured or displayed, it's going to have that N for newtons. So what we would do here is we would plug in the amount of force used, the 5,200 newtons, into our formula where F is, and then plug in the 20 meters where distance is, and we would just multiply them. So in the Edpuzzle, go ahead and put in what 5,200 times 20 is. And that's how much work was used to lift the steel beam. All right, one more example, same equation. A mechanic uses a hydraulic lift to raise a car to change the tires. The car has a mass of 1,200 newtons, and the car was raised 2 meters. So we're going to take the values that we know and plug it into the equation and then solve. So its force, or its mass, is in 1,200 newtons. So that would be in the force right here. And then the car was raised 2 meters, so that gets plugged into the distance. And then we just multiply because that's what our formula tells us to do. And that tells you how many joules of work was required or was accomplished by moving the car. Work is measured in joules. So work is measured in joules and force is measured in newtons. And that's it. Y'all have a good day.